This is the second lecture on Bessel differential equation. In the first lecture, we have introduced Bessel differential equation and argued that x is equal to 0 is a removable singular point. So we applied Frobenius method and found that the roots of the initial equation is m is equal to plus minus alpha and we found that the coefficient differs by 2 order in the power of x. So there are two series, one starts with c0 then c1. That is, this series is like this: c0 plus c2 x square c4 x to the power 4 multiplied by x to the power m, and another series is this and c1 is 0 if alpha is not equal to plus minus half. So for all other values of c alpha, c1 is 0. So this series may only occur for alpha is equal to plus minus half, and even for alpha is equal to plus minus half, we shall show later that both the two linearly independent solution can be obtained from this one. So we are neglecting this odd series all along. Then we said that for integral as well as non-integral values of alpha, the solution of Bessel differential equation is in the form of infinite series, which is unlike the other three discussed earlier. In all the three cases, due to some special values of alpha, we get a polynomial solution. The truncation was obtained, but in the case of Bessel differential equation, there is no truncation, and we have shown in the last class that in the asymptotic region, Bessel differential equation has an dumped oscillatory behavior, which indeed guarantees its convergence in the asymptotic region. Now we come to the series for Bessel differential equation. So we use this recurrence relation, and from using this recurrence relation, we obtained C2 in terms of C0, then C4 in terms of C0, and we generalize this as like this. And now coming to the this term, you note that m may not be an integer. In the other cases, in the other three differential equation, m was found to be integer, but here m is not an integer, so we cannot write factorial notation straightforward, but we use the gamma function. The gamma function, gamma of n plus 1, has the property is n into gamma n. So we can write gamma of m plus k plus 1 as 1 m plus k gamma m plus k, which can be written as m plus k gamma of m plus k minus 1 plus 1. So again it can be written as m plus k into m plus k minus 1 gamma of m plus k minus 1. Then we can continue this part, and we can continue this to write gamma for this part. So ultimately the value of this will go on decreasing, and this process can still be continued until we land up with m plus 1 term. And if we go on further and we adjust the this term, so m plus k, we write this the term in the reverse order, m plus k minus 1, and write to m plus 1. We rewrite it as m plus k ultimately it becomes m and the numerator can be written as gamma m plus k plus 1 and the denominator can be written as gamma of m plus 1. So this part can be written as minus 1 to the power k C0 gamma of m plus 1 to the power 2k k factorial gamma of m plus k plus 1. Now the choice of C0, one uses C0 as one uses the value of C0 as 1 upon 2 to the power m gamma of m plus 1. If we write this value of for C0, then we see that this gamma cancels with this and we have this is minus 1 to the power k 2 to the power 2k plus m factorial k gamma of m plus k plus 1. So we get the series for it. So for a given value of alpha, the series is obtained as like this. Y with m is equal to summation over k is equal to 0 to infinity c of 2k x to the power 2k plus m, where m is plus minus alpha. So if we write the value of this, we get k is equal to 0 to infinity minus 1 to the power k minus 1 to the power k. In the numerator we have k factorial gamma of m plus k plus 1 factorial and x by 2 to the power 2k plus m. Because this is 2 to the power 2k plus m and x has the same exponent. So this is the series. Now we define Bessel function of first kind as the solution of Bessel function which can be obtained by Frobenius-Fuchs method. So this is known as Bessel function Jm of x. This is known as Bessel function of first kind. Note that Bessel function of first kind, we define it as the solution of Bessel differential equation which can be obtained purely by Frobenius method. Now you know that m has two values, m could be plus alpha or m could be minus alpha and depending on the value of m we will get j alpha, j of minus alpha. So the Bessel function of first kind may be defined like this. J of alpha x is equal to k factorial. This is gamma of k minus alpha plus 1, and in the numerator it is minus 1 to the power k, and sorry, it is plus, and x by 2 2k plus alpha. This is the for m is equal to plus alpha, and for m is equal to minus alpha we have j of minus alpha is equal to k minus alpha plus 1, then x by 2 to the power 2k minus alpha. These are the two solution Bessel functions. Both are the Bessel function of first kind of order plus alpha and minus alpha. We now consider a special case that alpha is an integer. What happens to alpha is equal to integer? If alpha is equal to n is equal to integer, what happens then? Then gamma of k plus alpha plus 1 is simply k plus n factorial, and in which case Bessel function of integral order n becomes this is k factorial k plus n factorial minus 1 to the power k x by 2 2k plus n. Now we are coming to j of minus alpha. For m is equal to plus alpha is equal to n we have, for m is equal to minus alpha is equal to minus n we have gamma of k minus n plus 1 is equal to k minus n factorial, and consequently j of minus n of x is equal to summation over k is equal to 0 to infinity minus 1 to the power k k factorial k minus n factorial x 2k minus n. Now you see that k ranges from 0 onwards, and k and n both are integer for integral order of Bessel function. Say n is equal to 5, then for k is equal to 0 it is negative integer whose factorial is not defined. This continues right up to k is equal to n. So the first contribution here is not from k is equal to 0, from k is equal to n, in which case for k is equal to n this term is factorial 0, and the other higher contribution are defined. So we rewrite a term that k minus n is equal to L, in which case the sum may be written as j of minus n of x can be written as summation over L is equal to 0 to infinity and k is equal to is minus 1 to the power k is equal to n plus L. This is n plus L factorial, and this is L factorial x to the power 2m, then this is simply 2L plus n. Now if we take minus 1 out, the rest of the thing is j of n. So we write it is minus 1 to the power n Jn of x. So we see that for integral values of alpha, j of plus n and j of minus n are not linearly independent. This is a dependent solution because from this we can get this just by a phase factor. It is interesting to find out J0 from here. If we put J0, that is n is equal to 0. So J0 is n is equal to 0, and we get from this series it is summation over k from 0 to infinity minus 1 to the power k. Then in the denominator we have k factorial square, and here we have x by 2 to the power 2k as n is equal to 0. So putting k is equal to 0, we get this is 1, this is 1, this is 1. Putting x is equal to 1, we get this is minus, this is 1, and this is x by 2, x square by 4. Then putting k is equal to 2, this is 1, this is 2 factorial square, so this is 4, and this is k is equal, this is 4, so this is 2 to the power 6. Here 2 factorial square, so 2 square, and here we have 2 to the power 4, so 2 to the power 6, x to the power 4. And this continues. If we put x is equal to 0, it is 1. So J0 of 0, J0 of 0 is 1. Now we calculate another one, J1 of x. J1 of x is summation over k is equal to 0 to infinity minus 1 to the power k. Then we have this expression k factorial, k plus 1 factorial, x by 2 to the power 2k plus 1. For k is equal to 0, k is equal to 0, this is 0, this is 1 factorial, this is 1, this is x by 2 simply. Then this minus sign, k is equal to 1, this is 1 into 2 factorial, and this is 3, so 2 to the power 4, 2 to the power 4 x cube and other higher order terms. And we find that j1 and 0 is 0. This is only j for integral order of Bessel function, only j0 and 0 is 1, and all other jn's are 0 at the origin. It is instructive to show the graph of the Bessel function. J0 starts from here 1, and this is J1, J2, they starts from as like this. Now coming to the Bessel function of factorial order, we shall consider this series expansion, and we shall consider few special functions. So these two relations will be of use, so we write this for future use. So j of alpha of x is equal to summation over k factorial gamma of k plus alpha plus 1 minus 1 to the power k x by 2 2k plus alpha, and j of minus alpha of x is equal to summation over k is equal to 0 k factorial gamma of k minus alpha plus 1 minus 1 to the power k x by 2 to the power 2k minus alpha. These are the two series. One is for m is equal to alpha, other one is for other one for m is equal to minus alpha. We put alpha is equal to half, so j of half. J of half, if we put this in first term, this is factorial 0 and alpha is equal to half, so this is let me write with the bigger font. K is equal to 0 to infinity minus 1 to the power k. Here we have k factorial gamma of k plus 3 by 2, because the alpha is half, and we have x by 2 to the power 2k plus half. We take this out. So we write it as 2 by x to the power square root, so that this will be 2k plus 1, and we have gamma of k plus 3 by 2 x to the power 2 by 2k plus 1. Now this is 2 by x, then for k is equal to 0, k is equal to 0, this is plus, this is 0 factorial, and this is gamma 3 by 2. Gamma 3 by 2 x by 2 to the power 1. The next term is comes with the minus sign, and here we have 1 factorial times gamma of 5 by 2 factorial, and this is x by 2 cube. The next term is with plus sign, 2 factorial gamma of 7 by 2, and then we have x by 2 to the power 5, and these terms. Now for the evaluation of the gamma functions. Gamma function, gamma 3 by 2 can be written as gamma half plus 1, so this is half times gamma half, and gamma half is root pi, so this is root pi by 2, as gamma half is equal to root pi. Now gamma of 5 by 2, gamma of 5 by 2 can be written as gamma of 3 by 2 plus half, so this is 3 by 2 gamma of 3 by 2, and for gamma 3 by 2 it is 3 pi by 2 to the power square. Coming to gamma of 7 by 2, this is gamma of 5 by 2 plus 1, so this is 5 by 2 gamma of 5 by 2, and gamma of 5 by 2 is this, so this is 3 into 5 root pi 2 to the power cube. So other things can be obtained, other higher gamma functions can be obtained, and the generalization is very obvious. So we use this here. You see that pi appears root pi appears in every term, so we take out root pi, so this is 2 upon pi x common. This is, in the numerator we have half, and this is x by 2. This half is from here, and this is x by 2. Then this is 1 upon gamma for, this is 3 by 2 square, and we have x by 2 cube from this term, plus 1 upon 3 into 5 upon 2 to the power cube, and we have x by 2 to the power 5. And similar terms. We write it 2 upon pi x to the power 2. This is simply x, and this term. This goes in the numerator 2, and these 2 makes it 6, so it can be coupled to factorial 3. There are, oh, I have missed here another term coming from factorial 2. This term I have missed, factorial 2, so this is 2. So this is 2 to the power 6, and this 2 to the power 3 is in the numerator. So in the denominator we have 2 to the power 3, that is 8, which can be made 2 and 4. So altogether this is factorial 5. So this is x to the power 5 by factorial 5. Now it is our known friend. This is sin x function. So the result is 2 upon pi x sin x, which is the value of j of half. Now coming to j of minus half. For j of minus half, we shall use this expression, and j of minus half in this case it is half, so this is, and this will be minus. Now if we take this out, this factor is this, and this is half. Now we write the series expansion. For j of minus half. So we have 2 by x under root, and then first term plus, so this is 0 factorial and half factorial, so 1 upon gamma half, sorry, this is first term is gamma half, k is equal to 0, and this is 1. Then second term is minus 1. This is 1 factorial, and this is gamma of 3 by 2 times x by 2 square. Then third term plus 1 upon 2 factorial gamma of 5 by 2 x by 2 to the power 4. Now we write the value of this. This is, so taking root pi common, we write this term is simply 1. Gamma 3 by 2 root pi has taken care of, and this value, this half will go in the numerator, so this is x square by 2, which can be written as x square by factorial 2. Now coming to this part, this 5 by 2 is 3 plus 2 factorial, then this part gamma 5 by 2 is 3, and then 2 square in the numerator at x by 2 to the power 4. Sorry, this is 2. So this cancels 2 power of x, so it is x square, that is 4. So this all together makes it this part is x to the power 4 by factorial 4. I hope the simplification is understandable to you. So we write it as x to the power 4 by factorial 4. Again, the quantity within the third bracket is a known friend, 2 upon cos x. So we see that for alpha is equal to half, j of plus half and j of minus half are linearly independent. So Bessel differential equation, being a second order differential equation, can have at most 2 linearly independent solutions. Both of them can be obtained from the series starting with C0 by putting the 2 values of m. Here we see that the lower root, although the roots of the initial equation differs by an integer, both higher and lower root gives 2 independent solutions. But when alpha happens to be an integer, only the higher root gives us a solution, and the lower root, that is alpha is equal to minus n, does not give us any linearly independent solution. So that much with the series expansion of Bessel differential equation. In the next class we shall proceed with further discussion on Bessel differential equation.